Okay, I would like to resume my session. So I hope everyone is in the same page as what we are trying to explain currently. So let me just share the screen again so that we will get on the same part. So of course, as always, if you have any questions, please feel free to ask. Okay, so you are at your own liberty to ask questions. Okay, with respect to my knowledge, I would like to help you out. So, I mean, as I already explained to you, NI has been LabVIEW has these capabilities. Okay, like simulation is possible, but further than that, what is the possibility? What are the possibilities are which could be come into fruition? So let us just have a quick discussion about before we get into the next topic. Okay, let us discuss about what is the implementation strategies. As I've already explained, let's say you have okay, you have done the simulation using multisim and LabVIEW co-simulation. Everything is working quite fine. And we have also seen in the from the program that we have a recorded data. Okay, we are able to compare the simulation and the recorded data as well, right? So what is the possibility next that instead of converting the whole code? Okay, so and some people will be like, lab is only simulation tool. I'll do the simulation here, and I'll move to embedded C. Okay, which is quite um, you could say it's resource intensive. Okay, it's a waste of resource. Meaning we have already having a tool which is capable of implementing real world components as well. Like so, right? So instead of re-implementing the redesigning the wheel, reinventing the wheel, okay, what we could do in this program is instead of multisim lab core simulation, you just replace it with the hardware. Okay, this code will basically generate the SPWM and the ways in which it will switch on and switch off these pulses, the values of the circuit components. Okay, the switch on and switch off characteristics will be desired by this circuit. And this one will be multisim hardware. In multisim software, there is simulation software which will um, describe the characteristics of the circuit. What you could do later is instead of this multisim core simulation, you could replace it with the hardware I/O. Okay, so top and bottom could be given to the digital pulse of, let's say, an optocoupler, which is in turn connected to a MOSFET. Okay, let's say, or there are some hardwares, okay, in National Instruments itself, okay, which is called as general purpose inverter control, okay, which will have all the IOs, okay, required to directly connect to a MOSFET or to a totem pole, bootstrapped driver circuits. Okay, so you could just give the digital IO to that circuit so that that circuit will drive the MOSFET. Okay, depending on how much current it will consume, whatever it is. Okay, even though people say MOSFET is a voltage control device, okay, even though it has a high impedance, okay, it's going to draw a certain current, okay, due to a leakage capacitance in the gate between the gate and the substrate. So that current and all should be supplied by a driver. That's why we use a separate driver or a optocoupler. Okay, so whatever is easy for you. So instead of doing this IO in a separate program, LabVIEW and its NI's hardware platform is capable of doing it with the graphical programming itself. Okay, typical kind of solutions offered by this platform is, okay, it could range from a transformer power system grid to converter rectifier topology. Okay, AC to DC converters. Okay, rectifier control could be done. Okay, or inverter drive could be created, DC to AC converters. Okay, you could also do a DC to DC converter. Okay, controls. and also control of a battery or charging for a solar array. So it could be any of this by using this GPAC. Okay, and this could be used to drive a motor or get data from get power from a generator, whatever it is. And the platform could be LabVIEW. Okay, LabVIEW could be the general purpose, the programming language for engineers and scientists. Now we have seen how easy it was to do much complex tasks. Okay, and the hardware from National Instruments called as Compact Rio platform. Okay, which has the flexibility of embedded system. Okay, of a processor as well as an FPGA inside. Okay, which is capable of um, sub nanosecond control loops. Okay, if you want to have some control, okay, with respect to nanoseconds, okay, megahertz, multiple megahertz, okay, processors with operating system will not be as faster implementation. Okay, FPGAs will come into picture. Nowadays, FPGA are being used in several of the instruments. The reason being it's much faster. Okay, now in order to process some calculations using a processor, which will take multiple cycles of the processor. Okay, FPGA will do the process, okay, with using these resources, okay, in single pulse, single cycle. Okay, such as a capability of a FPGA. Okay, ideally to program FPGA, people will go for a VHDL, but using NIS tools, you can program a LabVIEW FPGA using the LabVIEW programming language itself. The only thing is the compilation time will be slightly higher, right? So you can program FPGA using LabVIEW itself. You don't need to learn VHDL. So you can do real time, implementation of acquisition of a SPWM signal, okay, and control the actual hardware using the compact Rio, which the program could be written over here. And you could acquire the data using the oscilloscope and display the data as an SPWM. Of course, we could add an SP filter, no LC filter, and make it look much sine wavistic. Okay, but here we have decided not to do because we had to do some um, debugging. But yes, this is an actual signal, real time signal. Okay, which is a 60 hertz because we have generated a 60 hertz signal. Okay, here also we can see that we are able to measure a 60 hertz, and we have done a signal conditioning here. Actually, the peak to peak was something like 70 volts. Okay, so here we have used a voltage divider to reduce the voltage. There are several usages where you can use this topology of power electronics. Okay, it's not only for electrical vehicle. Okay, you could use it for multiple other things. Okay, like wind power, wind turbine, and renewable energy, solar grid inverters. Out of which we could focus on using for electrical vehicles, hybrid vehicles or automobile, trains or whatever it is. So I hope that sums it up. If you have any questions, please do put it in the chat box. Uh, I will be glad to uh, view them and answer them at a later point of time. But now we are going to go for next point of focus, that is electrical traction motor. Okay, we have now seen that how power inverters could be easily, designed and validated by using LabVIEW. Okay, one small example also we have seen, and other, you know, um, in demonstration example also we have seen, right? So now we are going to see about the current focus of traction motor. Okay, for electrical motor or for any application, there are several motors available, and new motors are also come into picture. Okay, so what are the options which are available with respect to NI environment? Okay, for the simulation of electrical motor is what is our focus is going to be upon. Okay, and of course, everyone knows electrical motor is a device which converts mechanical and electrical energy to mechanical energy. Okay, it's a primary component of electrical vehicle. Okay, there are several types of electrical motors into play for different types of electrical vehicle. Okay, so AC induction motor is a common motor found. The three-phase induction motor is found. Okay, apart from the switch reluctance motor is also found in some vehicles. So, what are the options of simulation NI offers? Okay, and what are the simulation options available? So, types of electrical motor for EV. Okay, historically, okay, take components like BLDC, PMSM. Okay, three-phase induction motor has been found, right? And switch reluctance motor is also found. Okay, so what are the options of simulation does NI offer? NI number one offers okay a LabVIEW electrical motor toolkit. Okay, so electrical motor toolkit inside LabVIEW for simulation. So using which you can give some inputs okay of voltage, okay voltage waveforms normally supplied to a motor, and the responses you could get back okay in form of current consumed or a torque generated, right? And when you have the model of the motor, okay, there are different types of model available, okay, which we will elaborate in a few more slides. And there is also an option of multisim lab core simulation again. Multisim lab core simulation is not only fixed for inverter design. Okay, so since multisim is electrical circuit simulation design platform, motor is nothing but a collection of electrical components. Okay, of course, mechanical design is also involved, but you could simplify it to an electrical circuit. Okay, it has nothing but an inductor, basically a winding. Okay, so stator windings, rotor windings make up the electrical model of a circuit. So you could basically build it, or they have already built the circuit for us, a model for us. This is nothing but an equation. Okay, in terms of spice, you could make use of both of them, and both of them has its own pros and cons. Okay, if you're just going to do an algorithmic validation, you could go for an electrical motor toolkit. If you want to simulate a BLDC or a PMSM or an AC induction motor, you could go for electrical motor toolkit. If you want to go for something a little bit different, you have a different motor with a separate um, model. Okay, or you want to create your own model for an own motor. Okay, and you want to do system level simulation. Okay, multisim lab core simulation will be an appropriate simulation tool, and we are going to see both of them today. Okay, how? First, we are going to focus on electrical motor simulation toolkit. Okay, electrical motor simulation toolkit is an add-on available for download. Okay, which can be downloaded and installed for LabVIEW. Okay, once you install it, if you have observed, electrical motor simulation will come under the electrical motor control and simulation palette. Okay, it contains motor simulation models of PMSM, AC induction motor, and switch reluctance motor. Okay, these are three models which it submits to us, right? Sorry about that. So yeah, so control and simulation, in control and simulation, under that you will have an electrical motor simulation. I'll close this off. And I'll save this for now. Yes. What does this offer? Okay, what does this electrical motor simulation toolkit? Since NI toolkits are not only with respect to software implementation, Okay, always there will be a link for hardware implementation in future as well. Whenever we tend to design something in software for simulation, we will always try to understand whether this simulation could be extended for real-time implementation as well. So NI topology, NI hardwares, basically there will be certain hardware which could interact directly with drives as motor drives, which could be able to collect data as well. So when we do a simulation, we will make sure that we will be able to get an actual hardware, okay, do the same, tests, whatever we did in the simulation. We'll try to compare whether whatever we have expected is appearing in the real world as well. If not, then what changes do we have to make? Okay, so we try to do that. Okay, so doing the simulation in computer is much safer than doing it in the hardware. So let's get it simpler in hardware, in software, then try to do the experimentation in hardware. So that way, not wasting a lot of time. So what does this electrical motor simulation toolkit offer? It contains a built-in motor model. Okay, motor equations, deployed inside the programming. What it could be used to do is it could test the control algorithms. Okay, maybe you might have designed an efficient algorithm to control the speed of the motor or the current, control of the motor, the push and control of the motor. Okay, maybe sensorless push and control or sensor or speed control, whatever it is. Okay, you want to test whether that algorithm which you have defined or you made it better is working properly before implementing the embedded system in real world to a real motor. You could test in these models to check whether it is performing in terms of current consumption or whatever parameter you intend to guide, whether it is very stable, how stable it is. Those kind of information you could collect from here. Test the algorithm, control algorithm. Then later point, some of these calculations would need to happen in real time, in real response rates. Okay, so instead of bring the real motor, there is a real time uh, simulation option is available. Okay, by implementing these models in an FPGA itself. Okay, so you could use FPGA for simulation as well to make the simulation faster and to make use of this speed of the FPGA to calculate values. It's going to be much faster compared to a computer-based simulation. And finally, it's a growing field for in terms of engineering. Okay, there is something called HIL. Okay, Hill stands for hardware in loop, where you'll have two hardwares. One simulates the controller and the other simulates the plant. Okay, plant in the cells the motor. Okay, where you can have the instead of having the real motor and real controller, you will simulate the aspects of the um, controller in one hardware using one hardware, and the motor parameters will be simulated in the other hardware. So the controller will be controller hardware. The hardware which simulates the controller will be connected. The IOs will be connected to the hardware which simulates the motor. The signals which will be normally given to the motor will be given to this hardware, and this hardware will be programmed in such a way that it will respond as though it's a motor. When you give it the voltage signal, it will give the torque signal as an output, torque waveform as an output, and that torque waveform will be proportional to how a motor will actually react. Okay, it's a mathematical model, HIL model, which is deployed in the real motor. The advantage is this will respond very quickly and very nearby to how a real motor will respond. Okay, the reason for doing this is, let's say, if you want to immediately replace this simulated motor hardware, okay, with a real motor, you could do so because whatever signal normally will be passed to a motor will be actually passed to this hardware as well. So let's say if you're passing a three-phase sine wave, okay, 230 volts hardware. If the hardware is capable of that, you will pass the signal to this hardware. Okay, this hardware will be having an appropriate IO to measure that 230 volts is passing. So this data will go inside the hardware. Okay, so when 230 volts, this waveform is passed. Okay, possibly we'll have a model inside. When this voltage is passed, how should I react based on the time? Okay, that calculation will be inside. Okay, so it will start building, it will start calculating what amount of torque should be given out as output, and it will give the output as though it is giving in the form of an encoder. Encoder is used to measure the position and the speed at which the motor is rotating, and that will be measured by the controller, and so on and so forth. So hardware and loop is a growing field now. Okay, I'm sure most of you will be knowing about it. You could build this. This contains a framework for all these things, which you can make use of and expand as your application goes on. So now you might ask, what are the types of models available? Okay, motor models, yes, different types of motors are available, but what are the types of models itself is available? Okay, depending on the complexity and depending on the rate at which you want to run the motor simulation, okay, whether you want a very quick run of simulation models, okay, depending on complexity, accuracy which you expect, okay, you have three models of motor models available. Number one is constant parameter model. Okay, second one is variable parameter model. Third one is FEA model. The FEA model is basically it's a I know mostly I've seen mechanical people get excited about this. Okay, FEA stands for finite element analysis model. Okay, so it forms a very accurate model of any system, mathematical equations of system, in order to replicate them in a programming environment or in real world as well. So depends on requirement, resource, and fidelity. Okay, fidelity means how repeatable the calculations occur. So you will have three different types of motor models. So first one is constant parameter model or linear model. Okay, it's a very simple model of the motor. Okay, just by giving some simple parameters, you are going to make it make the model of the motor appear. Giving some signal as input, it's going to process, calculate the data, and it's going to give you the output. Okay, it's not going to take much time to calculate anything. Okay, various parameters of the motor is required. That's the requirements, simple requirements. Resource, if you see, it requires very small amount of resource, relatively very small. Okay, calculations also, if you see, it's much like what we could do using hand. It's okay by taking a calculator and doing it, you could do it. Okay, but the rate at which you are doing it is going to be much higher. It's going to, if you do the same thing as a computer instead of using the um, handheld calculator to do it, if you use a computer, it's going to do instantaneous calculations every second or every millisecond or so, depending on the rate, you could do the calculation. Fidelity is how close it is to the real implementation. Let's say if I take a PMSM motor, okay, do a constant parameter model, I acquire the waveform, and tomorrow, let's say I bring a real motor and connect the instruments to it. I set the waveform, I set the RPM to whatever I set during the simulation. I record the data and I compare it to what has happened during the simulation. If I check it out, it's going to be distinguishable, very distinguishable. When I say distinguishable, it's going to be very different. Okay, what you expect in simulation would be very different than what will happen in the real world, because the number of parameters used is very less. Okay, you could enter it by using your computer itself, those parameters. So it's a not much used, but it's the easiest implementation. Second part is variable parameter model. Variable parameter model, on the other hand, okay, is going to be a little bit more accurate than a constant parameter model. The reason is you wouldn't take this parameter from hand, hand entering. Okay, it requires something called as RTT files or ANSYS motor model files. ANSYS, a mechanical engineer would know, it's a software used to create the model, okay, the mechanical model of any system. Okay, there is a software called as ANSYS motor design, okay, for electrical plus mechanical engineers to create the mechanical output. You could set the number of the material, okay, used in stator, rotor, all this information will be stored. So when you create the log of the same, okay, the whatever motor you have created, Okay, the parameter of the same will be stored in a file. Okay, access file. Or there's also a file called as RTT files, which is available at a website called as JMAG International. Okay, it's a company which is specialized in motor model creation. Okay, so it will contain information related to motors. Only not 2 to 3, 4 parameters. It might contain multiple parameters, n number of parameters. Okay, resources here. Okay, it requires intermediate amount of calculations. Okay, so which means it's going to require significant amount of resources. It's not that laptops and computers will not be able to process it. It will be able to process it, but amount of time taken for it to process a small amount of data is going to be very large. Okay, but it's going to be ample amount of times accurate than what you would expect in the linear model, because it's considering a lot of data, at least more data than what a linear model could expect. Here also the fidelity, even though better than constant parameter model, still it could be distinguishable. Okay, but somewhat you could, some people could be okay with it. Okay, in terms of accuracy, repeatability, and sensitivity. The last one is finite element analysis model. Okay, it requires RTT files. Okay, which describe the FEA models. Basically, FEA model, variable parameter models, it could use the same files. Okay, but some parameters may be ignored by variable parameter model from RTT files. But when you do an FEA model, all the parameters stored in RTT files could be caught. And resources required to simulate a motor, okay, it's going to take heavy calculations. And to simulate some amount of points, let's say 100 points, it's going to take a lot of time. Okay, when I say 100 times, it's with respect to, in terms of, let's say, 1 second of motor data from start to running time. Okay, you want to do a step response. That data itself will require heavy calculations. It may take more number of time to process it, which means it's going to take more number of resources. And for real-time processing, it will require more number of resources on FPGA also. FPGA is not something like a processor. Okay, it is going to create a digital circuit to do your processing. Okay, it's not a coding. It's it's a creating of a digital circuit. It's a fabrication of a reconfigurable circuit, and it's going to depend upon the amount of resources available in the FPGA circuit. And FPGAs are not going to come with infinite number of circuits. Okay, infinite number of reconfigurable components. So depending on the FPGA, sometimes some complex simulation would require more than 4 to 5 FPGAs. Okay, in a single board. It depends. But the fidelity, okay, so the comparison to real world, it's very, very close. Okay, it will contain all the parameters. Okay, to compare and say, okay, this is how it will react. RDT files, okay, could be downloaded from a website called as JMAG International. Okay, they contain motor models. Okay, if they don't have the RTT file for the motor you're expecting, you can always create an RTT file by using this website for software called as JMAG/RT software. Okay, you could check out that website, and if you want, you can try downloading it and checking it out. Okay, there are various resources available in the website itself. Okay, we'll not be focusing on that. Okay, so different motors could be, not all the motors contain all the simulation parameters. Okay, more options. Okay, in lab at least. Okay, so like for example, PMSM could do all three. Okay, if you see PMSM, constant parameter model, FEM model, variable parameter model. Okay, it reads the constant parameters. Okay, the FEA model can do RTD file only. Variable parameter model could do RTD file, ANSYS model file, or external model also. Okay, DLL file also it can do. So this is to simulate the motor response. Okay, later what they'll do is real reason to import the motor model in lab is to create a controller application, okay, to create a control system to control the motor. So they'll give certain control responses to the motor. Okay, the motor model, circuit software model. They'll check how the controller is responding based on the feedback which is received. Okay, and we'll check whether the control application is happening properly or not. The controlling electrical motor is happening. Then ultimately next objective is to simulate this in an FPGA in order for it to happen very quickly for a large number of time. And to create an HIL model, I told, right? So one hardware will say simulate an ECU, the other hardware will simulate a motor. Later, interchangeably, either they will replace the ECU with a real ECU, and the simulated motor will be there to check whether the ECU is working fine. Then later, what they'll do is they'll replace the motor, they'll replace the motor model hardware with a real motor, and they'll check whether the ECU is properly interacting, controlling the motor or not. SRM, system reluctance motor, has an option of linear model and FEA model. It does not have a variable parameter model. AC induction motor in this version of toolkit, okay, only has constant parameter model. Okay, there are no now the this electrical motor simulation toolkit is taken by another company called as Opal RT. Okay, they have circuit design parameters for other models as well. Okay, so they will have the toolkit, okay, which could be used to do that. So now we are going to see an example of a PMSM motor control. Okay, we are going to see from starting from the testing stage to demo on control algorithm stage and discussion upon simulating the same in the PMSM and the discussion about real-time electrical system, how the real-time electrical system will be designed. First, let's test the model, how to get the model inside lab environment, those kind of information. Let's see. So for this, of course, you need LabVIEW. Okay, here I have LabVIEW already installed. And apart from LabVIEW, you also need, critically, you need something called as electrical motor simulation toolkit. Okay, let's see what happens here. Okay, I deleted it, so I'll just replace it and open a new file. Here, if you see, we have something called as control simulation and electrical motor simulation toolkit. And my objective is to just do a small simulation of a electrical motor simulation. PMSM. And what I'm going to do is I'm going to do a simple simulation of a constant parameter model. So if you see, there are certain parameters which are required to make this simulation possible. Okay, in order to make the constant parameter model of the motor possible, okay, I need to give the parameters such as number of poles, the resistance, the rotor resistance, okay, then the inductance of a direct axis, the inductance of the quadrature axis, what is the flux linkage, a typical parameters involved in the motor, okay, permanent magnet synchronous motor. Okay, then voltage. Okay, this is instantaneous voltage. Okay, meaning at this point of time, what is the current voltage? Okay, normally we'll generate a waveform and we'll give the data one by one, right? Okay, so for PMSM, we need to give three-phase voltage. Okay, so instead of generating my own voltage, okay, so I have a function, okay, which is created inside. to generate the um, stimulus data for this wave data, no, voltage generator. So which I'm going to be taking from okay, as a function is available, okay, which I'll make use of. Okay, which will calculate and give me the voltage and rotor position. Okay, I'll drag and drop it for usage here. What will do is it will generate me the stimulus data. I just need to give the RPM at which this motor rotates. So based on the information, it will generate me a data, a waveform. Okay, it'll calculate and it'll generate. How many samples of point do I require to generate this instantaneous voltage? How many instantaneous points do I need to generate? That also I have to give it as an input. And what is the rate this calculation of this input is being done? DT in the sense they did time difference between different samples. So we're going to do something similar to real-time implementation simulation. Okay, so what I will get from this is I'll get the voltage and rotor position, which I need to give for the calculation of other parameters like current, ABC current. If we give ABC voltage, we give the ABC current in different um, range. And director axis current, quadrature axis current, I will get the torque. So depending on what your requirement is, you can give the data here. Okay, now I'm just going to stick to preset data. Okay, so PMSM parameter concept parameter models values. Okay, so number of poles is 4. Okay, I'm going to stick to a 0.25. And direct axis is 0.00262 and 0.00442. You might ask why these values. Okay, because next I'm going to show a demo on to compare the PMSM value with other models as well. I mean the concept parameter model with variable parameter model. This model is of which is of a motor with a file. Okay, RTT file is available. Okay, so we'll be able to compare how RTT constant parameter model varies with the variable parameter model and how it varies with FEA model. And the speed at which it rotates is going to be 1800 RPM. You can always reduce this and check it out. 1000 points. Then the DT, the sampling rate is going to be the sampling time per. This is going to be 2 e power minus 6. Can I say 2 e power minus 6? If you connect the frequency, it means 500 kilohertz. Okay, so the rate at which the simulation is running is assumed to be 500 kilohertz. So this is instantaneous values. These are all instantaneous values. Okay, so I will copy this, cut this. I will cut this, and I'll show you how the waveform will come as output here. Okay, I can create an indicator here to check out how the values will come out. So the waveform basically it will generate instantaneous values of voltage. Okay, each and every second, each and every 2 e power minus 6 values. Okay, these individual values will go inside. Okay, one after another, one value, single values will go inside. So this is not really a good way to visualize. Okay, what I can do is I can plot it as a waveform. But plotting in the sense, it should not be row column wise plotting. Okay, LabVIEW basically prefers row wise plotting. So I need to transpose this data. So to transpose, I have array function. I have transpose 2D array. And I can use this graph, waveform graph. And you can see this is the data which has been generated. And rotor position also. So if you see, this is how it's going to rotate. 1 second it will be here, and the other second the degree rotation will be in different direction. So based on these data, you are going to calculate how the circuit is going to behave. Let me paste it. So now I need to send this data one by one inside. Okay, so first the second, next, like that, individual seconds will be sent one by one. To do this in LabVIEW, we use something called for loop. Okay, this is again the programming methodology in LabVIEW. We need to learn how the LabVIEW's basics will work and understood. Okay, but it's not hard to learn as well. So I'll send the value of voltage one by one. The three-phase data, instantaneous value. And to do the calculation, I need to know what are the parameters of the motor. I'll give that as well. And next, I need to give the rotor position as well. Rotor position. And I will specify the speed here also. Here also we have specified speed. Here also we have specified speed. So I'll just pass the data from here to here. This arranging and all is not necessarily important in the short run, but in the long run, if you don't arrange your code properly, if let's say if you open after a few weeks, you'll not be able to understand, see what you have actually done. So it's in a professional way to do it. Even after 10 years or so, you could remember what you've done if you just look at it. Or you can always add comments to your code. Comment here, whatever it is. So like it's the basics of programming. So outputs, whatever you get is ABC current, three-phase current, um, DQ current if you need it, and the torque. And I need to plot this as well. So I can right click, create indicator. It says something like subway has something to be wired. I believe DT. At what rate this simulation is running so that I'll be able to calculate all these parameters. Everything is time bound. Okay, so this DT is also very important. So now the program is runnable. I'll run this program. And it says input array does not match. Okay, perhaps I should send it before rotating it. So only for visualization, I have to do a what is called as tan transpose, but I have to just send it directly. So I get the values like torque, ABC current, and DQ current. So this is voltage input. Next is going to be the output, maybe current ABC. Again, during visualization also, we need to do something called as transposing, because that's how the data is coming outside from this function. So visualization in LabVIEW follows a row-wise visualization. So this gives a column-wise output. We'll just transpose it to get the data. So this is the current data. Okay, initially some transient is there, but then it becomes steady voltage current being acquired. Okay, let's see DQ current. Oh, sorry, ABC current is something which we used to give here. This is the ABC current. That is the direct access voltage, DQX direct access voltage versus current. And you can also look at the torque. Okay, so if you look at this in terms of numbers, if you look at the array, it will not make any sense. Visualization is where things will become clear. So only thing you need is the graphing tool is available in LabVIEW, which could help you visualize it better. This is torque. So torque, this is how the torque will react. It is just an open loop response. Just switch on the motor and run some characteristics. There is no immediate change in the speed or torque or water. No control is being done at all. You just give some waveform as input, signals as input, and the response, immediate response, is what you get here. And this is just a constant parameter model. You can do like variable parameter model or FEA model depending on the support of the models here. So I'm going to show a demo of it as well. Okay, we have models here. Okay, so let me know if you have any questions, or else let's
Hello.
yes, yes.
Sir, normally we use the simulation tools like LabVIEW and Multisim.
Mhm.
We do some circuit analysis.
Yes, yes, yes.
Sir, when we compare the results with the actual circuit,
Hmm.
Do you expect to have some difference, or there will not be a large difference? Can you please?
Um,
Yeah.
as far as my experience goes, okay, both with respect to, because as you say, and I have also assisted in several academic lab setups as well. So small circuits, when I observe, okay, like an RC filter, or a Butterworth filter, okay, something like that, or even a motor simulation also, okay, I haven't seen very large differences. Okay, let's say if you want to do a frequency response, okay, so we normally use something called as a Bode analyzer, okay, which is available as lot of hardware is available in academic hardware is available in NI. So with that you can do the RC circuit, board frequency response in the multisim itself. Okay, and let's say you bring the values of R and C. Okay, so when you connect it, as long as the probes, okay, the whatever probes you use to make the measurements, they do not affect the value of the, the maybe resistor or capacitor, okay, it's going to give as accurate as possible. Okay, I know there of course there are going to be certain tolerances, okay, so which is going to be there. So instead of getting the peak exactly at let's say at the 3 decibels at according to calculations, maybe it will say 159. Okay, you may not get 159 in the real implementation itself. Okay, maybe you'll get 160, or some tolerance will be always be.
Uh,
So yeah,
yes. So the errors, or the deviation from the actual results are within
expected.
expect.
Within
Okay.
tolerant. Yeah, there will be some tolerances will be there
Yes. Yes.
due to measurement errors or whatever it is. Will be
Yeah.
always.
Okay. Thank you, sir.
But yeah, one more thing to add is it all depends on your application. Some applications will be tolerant towards that errors. Some will require you to have as accurate as possible. So depending on the measurements you make, the amount of hardware, the amount of resolution, the amount of sampling frequency you use, okay, it's going to be as accurate as possible. But if you put more requirements, test resolutions and stuff as increases, okay, the cost obviously is going to increase. So that is also going to be there. But the more resolution is going to be, the noise, okay, may also reduce the sampling rate. Okay, and some hardware will come with pre-configurable, filters and stuff. But yes, to answer the question, you might expect some differences.
Yeah. Yes.
Yeah. Thank you very much for the question. Any other questions? Okay, so if you have any questions, please do let me know in the comment section, or at the end you can obviously, actually, of course, you can ask questions. So this is with respect to a simple, common, constant parameter modeling. Okay, so I'm just going to explain you. I'm just going to give you a demo on other parameter models as well. So here is the program which contains all three parameter models for the same input. Okay, so you have constant parameter model, you have variable parameter model, you have FEA also. Okay, for which you are getting the current waveform as well as torque waveform, right? So all three will be running parallelly. If you see this wave function, in order to run this, okay, it takes fraction of seconds. But if I run this program, okay, it's going to run maximum time. The reason being, FEA model is running parallelly with all three models. Okay, so it's going to take the maximum amount of time. Now it may not be large because we're not giving a very large data to this. Okay, but it's going to take significant amount of time. Okay, 1, 2, okay, 2 seconds is taking. Okay, this is taking 0.2 seconds or something. Okay, or maybe 0.3 seconds. We have not benchmarked it. Okay, but it's taking significantly very less amount of time. But just because it's running this function, okay, it's running a FE analysis. Okay, so it's going to take a significant amount of time. Every time I run this program, okay, it's going to take 2 to 2.5 seconds to process it. Okay, and it will display all the outputs, the same display. Okay, the data, the input which you're going to give is going to be basically this VA, VB, VC, that is waveform. Okay, I can hide other outputs. Okay, constant parameter model is what we saw before. This is very, you can say it's a very ideal model. Okay, and this is how the real data will obviously not come, because it has a very simplified model of the motor. You have a variable parameter model of the motor, okay, which is much more different than what you'd expect in the real world. I mean, in the constant parameter model, the deviations are slightly, different. Okay, the torque is also almost same, but not much difference when it comes to torque. But current changes are a little bit drastic. But FEA model, on the other hand, if you see, it will be very similar to what you will expect in the real world. And it also has those distortions. There will be like lock-in effect will come inside. Every time it crosses the certain place, okay, it's always going to do that locking effect. So you're going to have some distortion when you make the measurement. It's not going to be a exact sine wave. And even FEA model also, if you see the torque also, if you see, it's going to be having some variations. So this is how you would expect in real world for a PMSM. So it takes into account several parameters. Okay, even temperature parameter data also it might take from inside. If you see the data output input, okay, it takes into consideration something called as RTT file. Okay, it's a RTT file is 1KSTE/RTT. If I just go to Google and just paste it in my Google, it's going to go to JMAG International. It's going to show me a three-phase PMSM motors, data sheet. Okay, it's a 1 kilowatt motor, 100 volts, 20 ampere. Number of poles is going to be 4. Number of slots is going to be 12. Okay, number of phase. It will have all this information into the file. Okay, average torque, LD, LQ, inductance, torque constant. Okay, several other information is embedded inside this RTT file. And they will even provide a Simulink file as well. Okay, it's not like you can use this only using LabVIEW. You can do the same thing using MATLAB also. Okay, the RTT file is available for download if you create an account and use it. There are several other motors available, okay, which you can make use of inside. Okay, they have added PMSM, three-phase delta motor, 75 kilowatt motor, and whatnot. Okay, there are several motors available. Depending on your usage, you can take it and make use of it. Okay, all you need to do is just read the file, from the, we have it as a file here, PMSM files. RTT files are available. Okay, two types of motors are available. We also have one more file called as JSC. I believe it's a, I'm not sure if it's an induction motor or not. Okay, but you can just paste it in the Google. Or maybe not. I am assuming that it is also a PMSM motor only because it's inside the PMSM file. Okay, you can try reading it, but it may not have the same folders what it's used to have. So no response. It gets data something like this. A constant parameter of models comes something like this. Okay, but FEA will be very large. Okay, so this is with respect to a simulation. Okay, so what we have basically did is we are just testing the model. Okay, whether the motor model is adequate, it is working fine or not, we are able to test it. Okay, for that we have given certain values and we are able to make it out. Next is testing the control algorithm. Okay, so when I say control algorithm, okay, there could be different types of control algorithm to control the motors, operation. Okay, maybe you need to control the speed at which the motor rotates. You need to control the torque. Okay, whatever it is. Okay, when you do so, you are going to use certain algorithms to do it. Okay, there are several algorithms in place. Okay, so most commonly for PMS, some people will prefer field oriented control. Okay, for that certain algorithms will be there, so it's like closed loop, set point will be there. Okay, they'll do some sort of calculation to make it possible. Okay, so how do we do the same using LabVIEW? So as an inverter control, first we create the circuit. Okay, either you make use of multisim to create the model, then test the algorithm out. Okay, like for so our inverter we need to do the sequencing operations. Here we have the model, we need to give the control. Okay, control algorithm testing. Okay, so here we have the for the same PMSM control. Okay, we can do the closed loop control of the motor. Okay, closed loop control in the sense the motor will be continuously running. Okay, we could give some set point value, like let's say velocity, like RPM, we can give the load torque, we can give. We can see how the response with respect to current or the voltage given by the the supply. All these things can be checked. And ideally, to control a PMSM motor, we require you can take an inverter, okay, with varying uh, output voltage, frequency, VVF ratio. If you want to control it, you can make use of it. Okay, the inverter model is also readily available in the PMSM itself. Okay, PMSM, not motor control toolkit itself. Maybe you need to control an induction motor or whatever it is. So how do we achieve it here? You can even try changing the temperature and check how the responses to the current and voltage appears. So developing of this code is going to take significant amount of time. Okay, rather, I'm just going to open it and show it to you. Okay, so PMSM closed loop simulation. So take time to open. So if you see, there are set points. Okay, everything, as I told, graphically you can vary the development environment. Okay, this is the professional way of making the controls and indicators to to emulate the real instruments. Okay, you can vary these values of set point and observe the data as well. Okay, this PMSM is basically it's going to be a um, six pole. It can be a six pole, or it can be a here you can vary the parameter models and you can view the outputs as well. So let me just run this program. So you can see this set point. So in the starting point, it took some time to start up. Then it's going to run like straight line. You can see the voltage, the current output, and here this is a, you could say it's like a inverter input to the circuit. Okay, right now it's running at 1500 RPM. You have set point here. Okay, so you have set it to 1005. You can set it to 1500 exactly. It's going to take some time to adjust, but it's still going to come in because there is a closed loop component here. It's going to arrange, and of course you're going to have a very small amount of steady state error. Okay, it's very tiny amount. Okay, 1499.96. Okay, this is 1500. It looks as though it's a very large difference, but as a matter of fact, it is not. Okay, you could have like you could disable the auto scale option and make it as minus 2000 to plus 2000. So see, it's very simple to similar to a straight line. So it could be misleading. People will say, okay, why this is very large steady state error? That is because it depends on how large you have zoomed in. Now I could immediately make it to, let's say, a 600 RPM. You could see that it immediately goes over there and settles down. And depending on that, the waveform input also has changed. This is actually an output of a sine wave. You could basically use a graph palette. Okay, so a zoom in tool. Basically, this is a PWM signal. A PWM generator is at play here. Yeah, this is a SPWM signal, basically. Okay, there is a plot legend. You could have an enable or disable. Okay, this is the output of the sine wave. Okay, this is what is going directly to the motor. So in this program, initially it's going to settle down, then it's going to settle down in the voltage, I mean the RPM which we give. You can also modify the program to show you the digital display as well. So this is the actual set point, 600 RPM, whatever you set. We can compare it to actual value, actual speed measure. It change 200, there also is going to convert. It also has negative values. Minus, let's say I said minus 1500. And the moment I click, it's going to apply over there as well. The sequence is going to change. Instead of RYB, here it's going to change RPY. Okay, those the program will take care of. And there are various type of other types of tests you can do. You can do inverter-based test as well. It's an ideal inverter. It's going to work the same way. You could always change it to an advanced inverter. Okay, where there is no fault. Okay, or if there is you can set this as an IGBT open fault. How it's going to change when the fault occurs in one edge of an IGBT, or a diode open fault. What happens when there's a diode open at one location, or when there's a both diode and IGBT open fault or IGBT short fault? Different types of faults you can enumerate and check. What would be the responses? And in that case, you can check the parameters whether your IGBT will be able to survive or whether your motors will be able to survive this current. Okay, even if for some amount of time, based on that, you could implement a program and you can include a hardware to open a relay. Okay, or some sort of safety mechanism. Plenty of opportunities available. What happens if this kind of situation arises? So do we need to implement a safety mechanism? These are the options of faults, possible faults here. Of course, there could always be other types of faults which could arise. Okay, so custom faults you need to take care. Okay, this is a closed loop control. So let's just check what they have done in the um, block diagram. So basically, this particular program, okay, makes use of something called field-oriented control. Okay, where what it takes into consideration is it takes into consideration the ABC currents. Okay, and it gives us a feedback to the program. Okay, the operation. And it also has set points like the RPM. Okay, whatever set points we say, okay, it will be set. It will be a closed loop operation inside. Okay, so inside the field area control, basically we control two operations. Okay, we could open the subsystem and we implement PA gains. Okay, PAD for three options. Okay, one is to control the speed, and direct axis current and quadrature axis current for both we are applying PAD. Okay, PA gains are applied. Okay, speed, IP, IQ. Okay, and limits also we are setting for speed. Okay, based on some calculations, this is being done inside. Every iteration, different values will come, and using the PAD controller, instantaneous PAD controllers will be done. So this field error control will give this error voltage. There is a point voltage will be given. Okay, and this voltage value, in order to make the appropriate closed loop, okay, so this will be converted into PWM based on the voltage input which we give, and the amplitude also will be given. A frequency, all this information will be given to this PWM function. This will give us the on state of the IGBTs, okay, gate signals, and this will be given to depending on what type of operation we have selected, inverter type we selected. These gate signals will be given to the inverter, the three-phase inverter model, along with the DC voltage, okay, the voltage of the motor run. This will simulate these parameters, and this voltage will be given to the, again, whatever you used, constant parameter model. Every iteration, the individual values will go inside, and the responses also will be recorded. And this data will be given to the motor speed and rotor position measurement based on the values of um, these values. Okay, it will measure the speed and the rotor position. And next time to not implement the control mechanism, we will be giving it as a feedback. Okay, this is simulation. And this simulation, if you see, it's running good. Okay, visually it's good, but this is not real time. Okay, this is running with respect to computer speed. Okay, sometimes we need to check the responses in real time, how fast it would respond. All these things we have to check. Okay, so computer responses may not be that adequate. So for that reason, what we will do is we will basically do something called as FPGA based simulation. Yeah, control algorithm is set. Our model is also set. using our model when we set the control algorithm, this is our computer itself. Sometimes you need to check how quick it will respond and all those things. So for that, what we'll do is we'll simulate the PMSM model on an FPGA target. Okay, so basically something like this. We'll be having a hardware, appropriate FPGA hardware of LabVIEW, which will be controllable by using LabVIEW. Okay, we will simulate the hardware, okay, in the motor in an FPGA, and the controller will be simulated in a processor based system. Okay, the FPGA will control the processor and you will be able to get the responses. Okay, there are several ways to do this, but NI has certain hardwares, okay, which will make it much easier. Okay, NI lab the FPGA targets will be there, okay, which does not only have an FPGA inside but also a processor, okay, typically an ARM processor or an Intel based processor, okay, which will be running a hard real time operating system inside. Okay, previously they used to run VxWorks based hardwares. Okay, but as time progressed, nowadays since most of them require cybersecurity options, these hardware come with a Linux, real-time Linux, and of course, yes, Linux has a real-time option nowadays. Okay, real-time version of RTOS. Okay, RTOS, Linux RTOS is available. These hardwares come with the Linux, RTOS version of Linux. There are several hardwares here. We are going to use them. And out of that, some of the company controllers here are used for very different types of application. Okay, industrial controllers used for image processing, visual vision inspection. Okay, USRP is a software-defined radio platform, totally different operation. And RF instruments separate. Obviously, it is not used for this purpose. So these are eliminated. The other components are ideally used for, depending on the scale which you are talking about, it's going to be used for HIL based systems. Okay, so let me enumerate on how that will be done here. So for that we require a hardware. We are not going to we do not have a hardware here. So rather what we'll do is let's open the program. Okay, so let me just open the code. Okay, it will take some time, but yeah. So if you see, there are two models available, motors models available. Okay, so different cards will be available inside which contains FPGA. Okay, this hardware is called as PXI hardware. Okay, NIPXI. Okay, which is mostly used for HIL or for test and instrument operation. Okay, for high channel count or with tight synchronization options. Okay, it's basically a computer meant for test, control, and instrumentation. Nowadays, it's used for HIL option as well. So ideally, if you see, this is a controller, okay, which will be running under a PXI hardware. PXI hardware will be RT. Okay, RT means real-time controller. And you might be wondering how to program a real-time hardware. Okay, of course, as I told, LabVIEW is used to program FPGA. Okay, and LabVIEW also has support for programming real-time hardware as well. Okay, we don't need to learn embedded C as we used to do, previously. The same program what we do for simple programming addition, okay, it's the same, the graphical system could be implemented to program an RT computer as well, real-time computer. And real-time computer, it is something, like a PLC SCADA, but much more powerful. Okay, PLC SCADA is basically, this is in a PC, there's a PC based controller. Okay, but this could do much more than what a PLC SCADA could do. It's much faster, okay, and has more options. So if you see one hardware, this hardware, the program here is intended for RT programming. Okay, RT means real time. Okay, if you see this says RTPXI is runs under RTPXI. This will run under the hardware, okay, in an embedded system setting. This is something which is used to program embedded system. Okay, and here what happens is this will get data from as a feedback from the hardware FPGA. Okay, some the measurements, it's used to simulate the measurements. Okay, this is used to simulate the measurements of voltage, current. Okay, this is used to simulate the effect of a ECU. Okay, ECU, what it will do, it will take the measurements, current measurements from the motor. Okay, calculate certain parameters to make decision on what to do next. Okay, so it will make the measurements. It will calculate the FOC. So if you see, it's given as an input to field oriented control. Then, based on the calculation, you're going to have set point, and that set point is going to be given to back to the motor with ECU. Okay, so this motor basically it contains the inverter as well. Okay, this will be the ECU. Okay, the closed loop system will have the ECU, and the FPGA inside. Okay, will be having the switching on and switching off operation. So instead of building an actual hardware with FPGA, inverter and stuff, what you're going to do is we're going to do a software implementation of the same. So that's what is happening here. So this code is basically the FPGA model of your inverter and your motor. So this FPGA will generate the control signal, okay, of the gate signal. Okay, that data will be given to an inverter. Okay, inverter, there's no real inverter here. There's a model of inverter, FPGA model of the inverter. Okay, so if you see there is a model of FPGA, inverter in the FPGA program. This is an FPGA program. Okay, so you give the input of this signals to FPGA. It will calculate how the FPGA will respond. It will give the voltage, and this voltage data will be given to the simulation loop, which contains the motor model, and it will calculate the real-time effects of the motor. It will calculate very so fast, much faster than in real time than how your computer will respond. Okay, so the responses will be in real time since the FPGA is taking care of the calculations. Yeah, of course, it depends on the complexity of how your motor is going to be, parameters are going to be. If it's a simple model, it's fine. If it's a very complex model, you'll be requiring a FPGA with much, more LUTs, lookup tables and stuff. So here we're using a hardware called as PXIe786R. Okay, 7868R. So it has a very large footprint. Okay, so this is a FPGA simulation of the motor. So I hope if you have any questions, please let me know. Or else let's lastly discuss about the. Just give me a moment. Fine. Okay, this is until the FPGA targets. I mean, this is until the FPGA simulation. HIL is a totally different game. Okay, so right now you're doing both of the simulation in the rear in the same hardware. Okay, but let's say you want to interchangeably, you want to let's say simulate a motor instead of ECU. If you want to simulate a ECU instead of a motor. Okay, so in that case, you need to separate both of them into different hardware. Okay, so in most of the systems here, both RT and FPGA will be the same hardware itself. Okay, so Rio hardware it comes with both processor and FPGA in the same form factor. Single board also comes with the same form factor, and this all will be connected to something called PXI. Okay, NIPXI. Okay, which it makes use of compact PCI port behind a instrument computer. In short, PXI is an instrument computer which comes with multiple PCI buses. Okay, in order to make data transfer much faster. So real-time HL system will contain, the different hardwares will contain different models. Okay, engine model or a motor model, a fuel system model. Okay, each of them will have, and all of them will be communicating with each other as well. So here in this, for example, for example, here in this case, they have done a total HL of a car itself. Okay, so in this case, it's a hybrid vehicle, so they'll have both of this information. So in this case, if you take this is it contains the motor, the model of the hybrid bus. Okay, in this case, okay, in this uh, hardware depicts, okay, the simulation of a vehicle. Okay, this vehicle, this depicts a ECU. So I'll separate this is the motor, this is the ECU. Okay, they have used different hardwares. Okay, this is done by one of our clients. Fine. So this is with respect to the electrical motor simulation. Okay, the electrical motor simulation not only gives you options, okay, for just simulate and run, not and finish it off. No, since it's used by several, clients of NI. Okay, and of course, National Instruments. I hope everyone knows what National Instruments as a company is. As I've already explained to you, LabVIEW is used in several fields. Okay, they would require supports like this. So several companies would require, real-time test platform as well. So solutions should be required in that case. Okay, so they're not going to only stop with the simulation in the software alone. Okay, they would require, to implement it the same way, and furthermore to do integration testing. Okay, check how the hardware will respond in real time. So not only does it stop with computer execution, okay, you could do with RT, real time computer, and also to FPGA based hardware. So I hope that was clear for us. So if you have any questions related to this, let me know. Or else we have one more way how we can make this simulation environment possible. So I hope there is no questions as far as now is concerned. So in that case, let us enumerate the one more way of doing things. The next methodology is quite simply, let's say you don't have an option. You have only a PMSM motor, you have a synchronous switch reluctance motor, or you have a three-phase AC induction motor. And of course, you can do an induction motor also as a simulation. Okay, induction motor also comes with other options. Okay, you could do open loop simulation of AC induction motor. Okay, so if you see, it also has the voltage input. You can see the current output, electromagnetic torque, and you also have like a constant parameter model. Okay, where you can do a closed loop system. So it takes some time to open. So if you can see concept parameter model of the motor is here. Okay, here also you can set the set point for three-phase induction motor. Okay, how much ever you set it, okay, it's going to be appearing over there. Okay. So here in this advantage, this has a variation of changing stator and rotor temperature. Okay, in this case, you do a V by F ratio. Okay, VF ratio, variable frequency, variable voltage. Okay, basically internally there will be an inverter inside, and that will control the voltage output. And this also has all the the same methodology. Okay, after you do the simulation using computer, you do it using FPGA hard target, then you can proceed for HIL. So one last implementation methodology is multi-sim way. Okay, so let's say you don't find your own motor. You want to go for various types of different types of motors. Okay, here if you see three options are available, but in terms of multi-sim, okay, since multi-sim is a circuit design platform. Okay, there are options related to electromechanical design platforms available inside. Okay, electromechanical implementation of motors are available. Or if you don't find it, you can basically build your own model. Okay, and you can build equations. So, okay, you're going to find lots of other options, okay, related to motor implementation. Starting from brushless DC machine motor to there are other options as well. You can also even find a stepper motor, synchronous permanent magnet machine. Yeah, of course, these are not equal to EV. Okay, these are not all of them are relevant to EV, but motor simulation is possible inside. Fine. So in this case, okay, you're going to build. You can build possibly build a BLDC motor here. Okay, where you'll give the 12 volt input. Okay, and you can find there is a H bridge, inverter control using the uh, inverter option, and in the center you find the motor. Okay, so after giving this input to the motor, okay, you could find that you could see that you have a current measurement operation option. Okay, there is also encoder option available. Okay, so in this case, you give data from LabVIEW. Okay, so it's a LabVIEW some simulation option available. Okay, so based on the control pulses, you are going to measure a different speed. Okay, the encoder data will be different. Okay, whatnot. And of course, you will develop a LabVIEW code as well to control the do a closed loop system. Okay, based on set, this is the set current value. Okay, based on set point, you will vary the speed at which this pulses will be generated. And the LabVIEW code for the same is available here. Okay, I'll just demo it for now. Okay, developing this would take a very long time, and it will not make any significant effect here. So we'll just show a demo with. So you have an ideal H bridge as a multi-sim model. Okay, which contains HPG inverter. Okay, you have four switches, and in between you have the motor. Okay, you could find all these components in the component palette. So this is the motor model and inverter model. Okay, here I have this. You can find the same model in. You can go to place component. You could find here something called electromechanical, and you find there's something called machines. So we are basically using a DC permanent magnet machine. Okay, you could see that there are models, parameter values also available. Okay, armature inductance, resistance, speed constant, torque constant. Okay, depending on the motor model, you can change these values as well. And you could find an incremental encoder, the DC component, and I believe it will be in motion controller or sensors. Okay, so you have an incremental controller here. And you have this multisim lab core simulations, terminals, okay, after which you can basically, you know, do the control by writing the algorithm and testing it out. So I run this code. Okay, you could see the switching on and switching off of the. It's happening so fast that you cannot see the U2 and L1 acting at all. Okay, but it happens so fast, so you may not be able to see it. So this is the set point, and you also see the motor current speed as well. So here also closed loop comes into action. So if you change the value, it's going to make some small dent at the beginning. No, it's going to have a overshoot or undershoot. The code is basically it has a PA controller, okay, which is going to be converted into a PWM generator, SPWM generator, and PWM generation, and this in turn is going to be given to um, the full bridge controller. Okay, based on positive or negative, it's going to send the PWM generator to one pair or the other pair. And you give it to the model, and that's going to take care of it. And you measure the values of speed, okay, or the speed. It's just going to give radian per second. You are going to convert it into speed, and that data in turn you are going to give it to the PI controller. Based on set point you gave, okay, it's going to calculate the error, and the PI controller is going to do the closed loop. So this is with respect to multisim implementation. So you might ask, who has used this? Okay, I could give one example, okay, very quickly. So one case study, what I can give is a company called as Subaru. Okay, they have used the NI FPGA plus NI's hardware and software platform along with Multisim to make this a reality of testing motor ECU with without having a motor action in real time. Okay, the advantage of doing that, okay, it's a company called Fiji, okay, FIGA. Okay, they have Subaru model. You can Google it. So basically, what are the things they used is LabVIEW, PXI, okay, and FPGA cards and a stereo hardware. Okay, they had a test strategy. Okay, first they need to test it before actually fixing on a motor. So they have some test, plan available, and they implemented using LabVIEW. Okay, with which they were able to do the fault insertion. Not all we did, right? So they could do the same here as well. Okay, and they are advantage to test their ECU before actually using that ECU on an actual motor. The advantage here is when they did the same thing previously, okay, they took 2,300 hours, but after they got experienced with the HIL format, they were able to complete all the tests in 118 hours. Okay, which was 20 times less time taken for than uh, the traditional methods. And also they were able to simulate the effects in various conditions like temperature, all those things could be simulated. And let's say if they find a bug and they fix the bug, okay, they could retrace it back by conducting something called as integration testing, or you know regression testing and all. They were able to do very quickly since it's all automated. So with that, let me just conclude the session. This is how you can do a full electrical vehicle tests for both validation for both inverter control as well as for electrical motor simulation. There are multiple things, like you can even do battery management testing or DC to DC measurement or charging station. Okay, there are several other aspects where you can focus on EV using LabVIEW. Okay, so with that being said, let me know if you have any questions of any sort, or else we could conclude this.
Dear participants, if you have any queries, please unmute yourself and ask the sir. You can also type your queries in the chat box.
So if you don't have any questions, yeah, I think. Okay, so if you don't have any questions, okay, you say
If you, yes, sir, shall we conclude the meeting, sir?
one question is that I will address it and we can conclude, sir. So in EV side, which simulation is best fun for whether or LabVIEW or MATLAB? So, sir, to answer your question, there is no best tool when it comes to anything, sir. Like if you see, MATLAB and LabVIEW can be used in hand. Okay, so if you see, there are some certain models like JMAG, RTT files are there, right? So even for HIL, okay, to conduct the actual HIL to generate the models, okay, we actually use MATLAB, to generate the model, then conduct hardware-based simulation. The reason is very simple. MATLAB, is a very good modeling tool, okay, but the um, thing which it lacks is hardware integration. Okay, that's why people go for either DSpace, okay, for electrical based design, or LabVIEW. Okay, because LabVIEW has a wide variety of hardware integration. So we cannot never say that LabVIEW, but what application is better is LabVIEW has a very good integration with respect to hardware. Okay, so in real time measurements and real time testing, LabVIEW is the best. MATLAB, on the other hand, it is best to create the model, mathematical models, and to test it in simulation form. So that's how we can enumerate. But both of them are not enemies. Okay, you can also use both of them together to amplify the advantages. So in that case, thank you everyone for the.
Yeah, sir, if I can just take a quick question, sir.
Yeah, sure.
Sir, like uh, whatever computation the simulation tool like LabVIEW does, it is again based on the circuit theory, sir.
Um, Not only does LabVIEW do the same thing what circuit theory will do.
Yeah.
Okay, LabVIEW is basically a instrument simulation.
Yeah,
Okay,
yeah, yes.
yeah, it is used to, you can do mathematical computation, everything. Okay, the only difference is circuit.
Okay,
Circuit, what it does is, multisim does the circuit design.
okay, sir. Okay. Yeah.
Yeah,
Fine, sir. Fine. Yeah, yeah.
yeah,
Thank you, sir. Thank you.
yeah. So I'll post my number anyway, a number and my contact information. If you have any technical queries or any technical support is required, please do let me know. Okay, my name is Rajkumar. Okay, the number is 7448414136. The best way to contact me, however, is through mail. So if you have any technical queries for implementation or anything,
Sir, can you post your number on the chat
the
box?
chat box
Yeah,
already
yeah,
I
yeah.
posted.
I see. Yes. Thank you.
Yeah, so my name is Rajkumar. I work as a senior application engineer at VA Solutions. Okay, we are a alliance partner, okay, integration partner for a company called National Instruments. Okay, National Instruments is a company which specializes in providing solutions, graphical solutions for test, automation, control, HI. So thank you everyone. Um, I would like to conclude the session. Thank you very much for giving this opportunity. Um, for with the ACCET College, Alagappa Chettiar. So it's been an honor to be a part of this FPG program. So So I remember few months ago I contacted ma'am. So it has come to the fruition only now. But it took a while, but still it happened. So thank you very much, ma'am, and thank you very much, sir.
Thank you, sir. Thank you so much. Practicing is an important aspect of any professional course. Engineering is no exception to this. Preparing industry-ready graduate is a dream of many institute. In this chase of dream, this session will be very helpful. Our speaker, Mr. Rajkumar sir, has so light on modern tools which equip us to practice engineers and help us to prepare industry-ready students. Thank you so much for your effort, sir. And the participant, thank you so much. Next section will start at 2:30 p.m.